everyone, this is Fiza friend from Group 316. Today's my topic is luminescence. Like absorption spectra, the luminescence spectra of complex molecule are blurred and devoid of fine details. This does not refer to the Shopsky line spectra, which are observed under the special conditions and which have so far found no applications in biophysics. The intensity, polarization, and duration of fluorescence proved that to be more informative than the wavelength of band maxima. The wavelength of band maxima are not so much informative as the intensity, polarization, and duration of fluorescence. The fluorescence emission of complex molecule is polarized even with a natural incident light. The theory of luminescence polarization has been worked out by Vavilov and Fluvilov. The exciting light is observed by molecules that are oriented in a special manner with respect to electric vector of light wave. After the light has been observed, the energy is emitted as a result of another electronic transition to which there correspond, generally speaking, a different polarization in the molecule, that is a different direction of the transition dipole. If the lifetime of the excited state, that is the energy transfer time, is short as compared with a reorientation time of the molecule, the luminescence becomes polarized. The degree of polarization is defined as follows in this equation. Calculation shows that the maximum value of P with a natural incident light for a fixed randomly orientated molecule 1 by 3. The rotational motion of molecule or atomic group of depolarized the fluorescence. Theory yield the Levishon-Perrin formula. The degree of polarization falls off with increasing mobility of the light emitting molecule and may serve as a measure of mobility. Radiation-less transition, which are responsible for the quantum yield gamma being less than unity, reduced to the conversion of light energy into heat. Important factor responsible for the decrease in quantum yield is the quenching of luminescence. It can be provoked by foreign substance or by the migration of excitation energy from molecule to molecule. The emission with subsequent reabsorption of light but a direct transfer of excitation energy due to the resonance interaction of molecule, which increase with decreasing distance between molecule, that is with increasing concentration. The condition for such an interaction is a strong overlap of absorption and emission band of the molecule. The resonance migration of energy occur in the interaction energy is great, that is by far exceeded the width of the electronic vibration zone. In the case energy transfer takes place rapidly and the effect of vibration may be neglected. In contrast to excitation spectra, which arises in the case of a weak interaction in the spectra of resonantly interacting molecule, no vibration structure in observed. Migration of energy brings about the depolarization of luminescence. A molecule that absorbs a quantum is oriented in some way in space. If the some molecule emitted light, it would have a certain value of the degree of polarization. However, during the time between absorption and emission, there can be repeatedly occur act of energy transfer the another molecule with a somewhat different orientations. After a certain time period has elapsed, all the excited molecule lose the original orientations and the emission become depolarized. It should be emphasized that energy migration is possible between different as well as identical molecules, provided that the absorption band of molecule of one species and the fluorescent bands of molecule of another species overlap. The studies of the specific feature of luminescence associated with migration of energy is important for biophysics. The transfer of energy from one luminescent part of the biopolymer to the another allow one to estimate their relative arrangements. The study of polarized luminescence yield information on the conformational structure and its dynamic on the mobility of macromolecule and of its individual group. The frequent use luminiferous or cyclic pi electronic system. For example, aromatic amino acid residue in protein emits luminescent radiations. Types of luminescence. First, fluorescence, emission of light after absorption of radiation. Phosphorescence, long-lasting emission of light after absorption. Third, bioluminescence, production of emission of light by living organisms. Fourth, chemiluminescence, emission of light resulting from chemical reactions. Biological applications. First, imaging techniques. Fluorescence microscopy, confocal microscopy, super resolution microscopy. Second, protein structure and functions. Fluorescence resonance energy transfer. Fluorescence recovery after photobleaching. Third, cellular signaling and dynamics. Chemical imaging, membrane potential imaging. Fourth, diagnostic tools. Bioluminescent assay, fluorescent probes. Bioluminescent process. Luciferin luciferase reaction, green fluorescent protein, firefly luciferase, Renilla luciferase. Biophysical techniques. Spectroscopy, example fluorescence, photophosphorescence. Second, microscopy, example fluorescence confocal. Third, imaging, bioluminescence, chemiluminescence. Fourth, spectroscopy, example fluorescence lifetime. Advantages: non-invasive, high-sensitive, real-time imaging, quantitative analysis. Next topic is myoglobin and hemoglobin. Hemoglobin and myoglobin are not enzymes. Their function consists in the reversible binding of molecular oxygen. Myoglobin serve to store oxygen for its subsequent utilization. Therefore, large amount of myoglobin are contained in organisms of whale exciting predominant underwater. Hemoglobin is the functional protein of erythrocytes which serves for the transportation of oxygen from the lungs to all organs and tissues and with participate in the reversible transportation of CO2. The properties of ordinary and allosteric electronic conformational interactions. The binding of O2 and the other ligands by the protein bear a close resemblance to the binding of substrate to the enzyme. The molecular oxygen penetrates into the interior of myoglobin and hemoglobin molecule, but it distinction to the substrate. It is not subjected to a chemical conversion. Sometimes myoglobin and hemoglobin are called honorary enzymes. Myoglobin and hemoglobin are produced in crystalline form. Both proteins have been studied in detail by X-ray structure analysis with a resolution of up to 0.28 nanometers, both in the oxygenated and the deoxygenated form. The presence in myoglobin and hemoglobin of the prosthetic group of the heme, which has specific electronic properties, allows one to study the protein by which of the spectrometry. Electron